ever look up at the sky and wonder how a satellite can just hang there, motionless, like it's pinned to one spot? Well, today, we're going to unpack the incredible physics behind that illusion, an idea that powers so much of our modern world.
So here's the plan. We'll start with the basics. What even is a geostationary orbit? Then we'll dig into the physics that makes it all possible. After that, we'll actually build the formula that defines it, and then plug in the real numbers for Earth. And finally, we'll talk about why it's so useful and where it just plain doesn't work.
All right, let's dive right in. The name geostationary is a pretty big hint, right? Geo for Earth, stationary for, well, not moving. But what does that really mean when we're talking about a satellite?
And this is where it gets kind of mind-bending. You've got this object screaming through space at thousands of miles an hour, but if you look up from Earth, it looks like it's not moving at all. How is that possible? It's not magic. It's just really, really clever physics. The whole secret comes down to perfect timing. Think about it like this. If you're on a merry-go-round and your friend runs around it in a circle at the exact same speed that you're turning, they'll look like they're standing still, right? A geostationary orbit is just the cosmic scale version of that. The satellite takes exactly 24 hours to circle the Earth, which is exactly how long it takes the Earth to spin once. So it stays locked right over the same spot. Now, pulling off this kind of perfect timing isn't just a happy accident. It's actually a super delicate balancing act between two of the most powerful forces in the universe. So let's get into the physics of how this actually works. A good way to picture this is to imagine swinging a ball on a string. If the string is really short, you've got to whip it around super fast to keep it from falling. That's kind of like a low Earth orbit. You're close to Earth, gravity is strong, so you need a ton of speed. But if you have a really long string, you can swing it much more slowly. That's our geostationary orbit. You're way farther out, gravity's pull is weaker, so you need less speed to stay in that stable path. So it all comes down to finding that one perfect altitude, that sweet spot, where the speed you need to fight gravity happens to give you an orbital period of exactly 24 hours. It's this perfect cosmic equilibrium. Okay, so that leads to the obvious question, how do we find that sweet spot? Well, it's not a guessing game. We can actually pinpoint the exact altitude we need by using a little bit of math. Let's walk through how we get there. So first, we start with the main idea. For a stable orbit, the pull of gravity has to be perfectly balanced by the centripetal force that wants to fling the satellite outwards. They have to be equal. Next, we need a way to talk about velocity that involves our 24-hour target. And we know that velocity is just distance over time, right? The distance is the circumference of the orbit, and the time is our period, t. So then all we do is plug that expression for velocity back into our first equation, do a little bit of algebra to get the radius r all by itself, and boom, we get this really powerful final formula. And now for the really cool part. We've got the formula, so let's plug in the actual numbers for our planet Earth and see what we get. Turns out, you only need 3 key numbers to find this very specific place in space. And what's so amazing is that it's just these 3 things. The universal gravitational constant, which is the same everywhere in the universe, the mass of our planet, and the time it takes for Earth to spin once. You put those 3 together, and they give you a single, unchangeable address in space where this is possible. So when we put those numbers into our formula and hit equals, we get an orbital radius of about 42,300 kilometers. But, and this is important, that's the distance from the very center of the Earth. To get the altitude, you know, how high it is above our heads, we just have to subtract the Earth's radius, which is about 6,400 kilometers. And that gives us our magic number. A geostationary satellite has to be parked about 35,900 kilometers up. And at that one very specific altitude, how fast does it need to go? The math tells us that too, a little over 3 kilometers per second. That's the exact speed needed to travel that huge circle in exactly 24 hours, hitting that perfect balance we've been talking about. Okay, so we've tackled the physics and we've done the math. But, so what? What does this mean in the real world? Let's talk about the incredible things this makes possible and also why you can't just do this anywhere in the solar system. The biggest application, for sure, is global communications. Because these satellites are so incredibly high up, each one can see a huge chunk of the Earth. In fact, you can create a network with just 3 of them, spaced out evenly, that can provide communication coverage for almost the entire planet, with the only blind spots being right near the North and South poles. But here's the catch. This trick doesn't work everywhere.
If you wanted to put a satellite in a stationary orbit around the moon, for instance, you'd have a problem. The orbit you'd need is actually so far away from the moon that it's outside what's called the Hill sphere, basically the zone where the moon's gravity is the main force. Out there, the Earth's gravity is stronger and it would just yank the satellite right out of its orbit. Same problem with Venus, but in that case, the sun's gravity would mess things up.
And that leaves us with a pretty fascinating final thought. We know the recipe for a geostationary orbit depends on two things: a planet's mass and how fast it spins. So could we put a satellite in a Mars stationary orbit? What would that altitude have to be? And would it even be stable? It really makes you think about how these same physical laws play out all across the cosmos.